All right, so it's recording now. So I'm going to go ahead and yeah, so it's recording now. All right, so let me. Okay. So today we are going to focus on a specific problem. So I'm going to go ahead here. And let's go to the website or not. So the plan today should be pretty. It's actually, I think, a pretty important lesson today. You're going to have a one homework assignment today, but it'll be very simple. There's no coding or anything like that for this one, although I think it's very important. So you should be seeing the calendar right now. I've updated the calendar kind of with the topics now, so I think this will be the structure of the course. Hopefully I'll have time to cover everything, but this is the plan. So I've given the introduction on Monday, right? So I've given the introduction on Monday and the motivation and everything of the course. Now today we're going to focus on something called the machine learning pipeline, and which is basically, you know, showing you all the little boxes, the sequence of boxes that we have to follow to solve machine learning problems. And then after that, we're just going to spend the entire class time on feature engineering problems. So the idea there is we're going to take all kinds of abstract problems, okay? And you can give me some problems, or I'll give you some problems. And basically, we're going to figure out what everything is. So I'll show you that process. This part of the process is something that is not structured in any way. It's not really structured. And so you just have to kind of learn it, right? You have to learn how to think about solving machine learning problems. That's really the main idea here with this, okay? So we'll basically just focus on these two topics today. Next week, as you know, it's Martin Luther King Day, so it's off on Monday. And then, as I said, we'll get into the algorithms. So KNN, naive Bayes. So you can see, because this is a foundations course, rather than an applied course, I mean, it's an applied course, but it's rather than, you know, just having that focus on problems, this one has a focus on foundations. We're going to look at the algorithms. And the algorithms are actually straightforward. As you'll see, we'll start with KNN and naive Bayes, which are two algorithms that we can easily implement in Python. So I always make the joke, right, that if you fell into a black hole and ended up in another place in the universe, right, you could still write a couple of machine learning algorithms from scratch, right? And so that's really the idea with KNN and naive Bayes, is that you can literally just understand, and by understanding these two, it'll start to give you an intuition of how all machine learning algorithms work, right? So you'll start to get they're you know, not all algorithms will be similar to these two, but they'll have, you know, there will be similarities, right? So it'll start to give you that intuition a little bit more. Okay, so in any case, I've updated the topics in the schedule. Okay, so that's been done. And also I added a couple of links of some of the software that we will need, right? So Python, obviously, Anaconda. This is something that you can install on Linux, on Windows, so certainly take a look at that. Weka is a tool that, you know, it's important to have available in your toolbox. You'll see why it's kind of nice. So we'll take a look at that as well. But in essence, WECA as a GUI interface, our focus this semester is actually on the algorithm. So we'll be using a lot of Python and, but easy Python. All right, so today then the focus is, as I said, these two boxes, the machine learning pipeline and feature engineering, okay? So I guess before I continue, are there any questions at all before we start with the topic today?
No questions.
No questions. Okay, great. All right, so if there are no questions, I'm just going to switch over to the whiteboard and talk, as I said, about these two topics. I really want to do this. I thought a lot about this problem set of, how to go from an abstract problem, whatever it is, to being ready, to having a data set that's ready for machine learning. That's really my goal with today's lecture, all right? And that will be the majority of it. Will just be, I'll take whatever problem we can think of, because that's the beauty of machine learning, right? That's, you can take any kind of problem. You will need to constrain it a little bit, specify it, simplify it a little bit, but in the end, you can frame it as a machine learning problem. Okay, so the first thing we're going to do, so let me grab my pen here. The first thing we're going to do is talk about the machine learning pipeline. So the machine learning pipeline, okay? And what that means is, you have, let's say you start at identify problem, whatever it is, you want to grab information from social media, you want to grab forensic data from a breach, you want to grab emails from an email server, images, information from sensors, whatever you can think of, information from the stock market, measurements of trees, animals, information, health information to make a diagnosis, pictures of 3D pictures of cancer scans, and it's just a sorting facility in a factory for fish, airplane engine maintenance sensors, all kinds of things, right? Self-driving cars. So this is the idea. We can take all of those problems. We can also take sequential problems, reinforcement learning problems, etc. But we need to identify what direction they go in, right? And so we need to understand. So the first thing is you usually identify the problem, okay? Then the next step is, if I just keep it as let's say just 3 boxes, it's gonna be the familiar input, right? And then there's gonna be, let's say, processing, right? And then there's gonna be output. So when you identify a problem, you need to identify these 3 things, right? So you need to identify, what are the inputs, what's the processing going to be, what is the output? And then obviously these things can be divided into more things, right? So now if we look at, obviously processing would be your machine learning algorithm, right? So the one that takes some data and makes a prediction, so the model. Okay, so this could be, let's say now, instead of processing, we're going to say the machine learning algorithm. Okay, so that you have that. What is the output? Well, the output depends on if it's, if you remember that classification, right, that we had on Monday. So we have supervised, unsupervised, and reinforcement learning. So in reinforcement learning, it predicts some kind of action to take. In supervised learning, it predicts some kind of a class. So if we're looking at images of cats and dogs, you know, is it labeled as a cat? Is it labeled as a dog, right? In unsupervised learning, which we will learn when we look at the k-means algorithm, it basically has to do with grouping things, right? So we're going to learn there that it assigns a type of a class, but it basically it's a class of belonging of, so it finds things that are similar between the samples and it groups them together, right? So that, but for the sake of simplicity, in most of the examples, and right now I'm just going to focus on supervised learning. Okay, so if we're focusing on supervised learning, we're going to focus on labels. We're going to focus on labels or classes. Okay, or classes, labels or classes, either one. Okay, and then now that leaves then inputs in what this is going to be. And usually inputs is where where this kind of explodes into a lot of things. Okay, so this will explode into a lot of pieces. Now there will be an additional piece here also called performance evaluation. Okay, so there's a piece here called performance evaluation. If you look at the calendar, I kind of pushed it back by like a week, and I think that'll be fine. But performance evaluation, or let's call it performance evaluation. And what does that mean? It means that we're going to evaluate how our model works. So that's very similar. Let's say you build, a new sports car comes out, right? So a Porsche, right? Or a Ferrari or something like that comes out, and they designed it, right? And then they build the engine and, all the suspension and everything. And then what do? They take it out to the racetrack, right? They take it out to the racetrack, and in the racetrack, they actually, they run it, right? They drive the car really fast and take all the turns and everything. And then at the end, what do they report? They perform, it did on average this number of miles per hour or per lap, it came in under this time. Whatever, they have some kind of a metric, some kind of a measurement of performance. So that'll be the same with machine learning, right? So that's one of the great things about this is that, you don't just have to trust me in what I say. This is something that you can always prove, right? You always have in the simplest form, you have let's say a data set. And you're going to split the data set into train and test. So you do this split randomly. The majority of the information, 80% of it or so, is in the train, 20% of it is in the test. So you're going to feed through the pipeline the training data. That data is used to train the model. Once the model is trained, what do? Now you apply the model to the other 20%, the one that you held out. So it's basically like two separate files. And then you apply it to that file, the test set, and then you use that to evaluate your model to see, oh yeah, my model actually performs really well. So it's like a grade out of 100, right? So it performs really well, or it performs, badly, etc. There are several metrics for that, for performance metrics. Those metrics are used across all areas of machine learning, deep learning, machine learning. And so they're basically going to be a constant. You can't have machine learning without these performance metrics. Now, there are other areas of machine learning that will have their own unique features. Sorry, not features, performance metrics. And these areas, like reinforcement learning will have its own performance metrics. Unsupervised learning does have its own performance metrics. And other things like translations, for instance, preparing corpora, etc. They have their own. But in general, though, we will use a set of metrics because, usually machine learning focuses quite a bit of supervised learning, okay? All right. So anyway, so here is the pipeline, right? So the pipeline now is starting to take shape. You still, as part of it, obviously, it's all dependent on the problem. And that's what I want you to understand. So I had a student, and he wanted to do something, and he described the problem to me, and then he said, oh, and I'm using a CNN. And it's great that he's doing that, but when I heard the problem and what he was trying to do, I actually thought maybe a CNN is not the appropriate thing for that. CNN is kind of a static, one sample at a time method. It might be more complex to do what he's trying to do. And I thought maybe this is a perfect candidate for a hidden Markov model. But, I have to learn more about the problem to be able to identify what kind of method I want to use. So just here, for instance, since today we're going to be doing some problems, I'll just add that we could also have sequence mining. And that way, we can say not just how to create the data set, but also which approach we should take, right? And those dictate then, of course, that it also dictates the kinds of features we're going to use, the kinds of performance metrics we're going to use, and so on. Okay, so basically the pipeline, it's kind of looking good, except that I said that this input actually takes, and that the input today will be the focus of the class. The input takes, or it could be divided into several steps, right? And the steps are, let's say, I'm just going to call it feature engineering. And that way I have a term to define after we define this pipeline. So feature engineering. And that basically, to me, that means I take a problem and I need to create a data set. So my output from feature engineering is a data set given some kind of abstract problem. So I have an abstract problem. So obviously the first thing would be actually to collect the data, right? So if that wasn't obvious, I should say, machine learning is about, not writing if statements and putting in the logic in there. If you want to do that, that would be more like AI heuristic rules. But in machine learning, it's all about the machine learning from data that it gets originally, and then data that it gets constantly. Data that it gets constantly in real time, for instance, and so on. So obviously first, collect data. And this might be that you just get a data set off the web, as we will do for a lot of our problems will be just like that. We're just going to collect or use data sets, because I don't really want to spend too much time in this class on actually going from raw data to data sets. Okay, so that's more of a focus of the applied machine learning course. But here we're just going to, take some data sets. Okay, so you collect the data, you have feature engineering, which will be the focus. Then after that, there's still a few things, right? There's still a few steps. We're just going to call it pre-processing. And pre-processing are just a lot of steps that happen sometimes with your features. You have to sort of organize the features. You have to do something called scaling of the features, which is basically like when you have some features, let's say that you have port numbers, right? So port numbers go from 0 to 65,000. But then you also have a number of bytes sent, number of bytes received. That's, could be thousands of bytes, right? And then additionally to that, you have, let's say, protocols. And protocols, let's say you're just using, 20 protocols. So it goes from 0 to 20. So the problem there is that you have too many scales, right? You have two, one that goes up to 65,000, one that went to bytes, so that this could be even more, let's say 200,000, and then one that's tiny that only goes to 20. So you can see those scales are too incongruent. They're too big, right? Too different. And so what you do is you really scale them so that when you scale them, they all go from 0 to 1. So it's all just going to be proportional, right, from 0 to 1, right? And that makes everything, the data, and that's a strong recommendation, right? So that literally could be a box of its own, because it's so important. And actually, this applies almost to everything in machine learning, from reinforcement learning to deep learning to supervised learning. Right? Once you do the pre-processing, the scaling, the other thing you might do is the feature. So remember, all of this is part of that input box. I just blew it up. And this would be the feature ranking or dimensionality reduction. Okay, dimensionality reduction. We will actually spend at least a couple of weeks on these topics, which are the ones I told you about: singular value decomposition and everything. And then finally, let's just say you have data set ready for machine learning. Okay, so that's kind of that input blown up into a bigger thing. Okay, a bigger thing. So now that I've kind of done this, let me read in the next slide. I'm going to redo the whole thing, and I want to fit in all the algorithms that are relevant. Okay, so that way, and I think that slide is an incredibly important slide. Okay, so let me do. So I'll do identify problem. That's what we will do today. Okay, so I'll point out within, remember, this is the ML pipeline. Okay, so that's the machine learning pipeline. Okay. Then if we look back at the previous slide, so now I'm just going to say collect data, feature engineering. Oops, what happened? Oh, here. Yeah, collect data. I'm trying to fit everything in here. So feature, because I think this is so important, and in particular because this tells you the why. Why am I, showing you this algorithm? Why am I showing you that algorithm? So always, if anything, do this on your own, print it out as a cheat sheet, have it, take a push pin, put the page on your wall, look at it, because this is extremely important. Okay, so the next box would be pre-processing and then scaling. And pre-processing, it's a lot of things, okay? So I'll show you guys a few things at some point of that box as well. But that could be a lot. Scaling. And I didn't even mention anything about managing the labels, but managing the labels would actually be in here. So actually, I want to use a different color for this. So I'm just going to list out for everything kind of what goes. So in pre-processing, labels, dealing with the labels, for instance. Something called one-hot encoding for deep learning, so one-hot encoding. right? But let me go back to the red. All right, so once we do, oops, once we go to scaling, feature ranking, and dimensionality reduction. So feature ranking. And dimensionality reduction. Right, and we will look at what algorithms go there, and that way you'll see, you know, the importance of it. And then finally, let's just say data set ready for ML. Okay, that's also a catch-all where you might have a few additional tweaks here and there. So data set ready for ML. Okay. After that, so that's sort of the input, right? Then we have choosing the machine learning algorithm. All right. So the ML algorithm. I can even make this one kind of a circle because it sort of stands out on its own. ML algorithm. Remember that it could be a deep learning algorithm. Deep learning is just a neural net. So algorithm. All right. So choosing the algorithm. Then we have at least two things, which are the labels and performance metrics, right? So these two here. Okay, so let me see if I think I can fit these. So labels for classes, and this in particular for supervised learning. But supervised learning, once you understand supervised learning, a lot of the boxes in the pipeline apply to the other areas. Okay, so that's the advantage. So labels are classes, and then finally performance. Oops. The last one, I'm just going to call it performance evaluation. Evaluation. So barely fit it in here, but you get the idea. So maybe I'll blow it up here. Performance evaluation. Okay, so this is the machine learning pipeline. Okay, so now if we look at, so if I go to the website, right? If we go to the website, now you can see all the topics, right? And you can see where all of these are going to fit in, right? So why am I putting these? So in particular, K-means and GMMs, that's actually unsupervised. So it would just mean the algorithm. Sequence mining, this will be a little bit different in the processing of the data, but still a lot of the elements of the pipeline apply. These three are just neural nets. This is reinforcement learning. Again, a little bit different, but some things apply. Chi-square, singular value decomposition, they have to do with the dimensionality reduction, performance metrics, and then KNN naive Bayes and other algorithms, they are the machine learning algorithms. You can see how these topics then tie in to that, that pipeline. So if now I go ahead and you know, there might be some topics that I just can't cover this semester, but they would also fit in there. All right, so for instance, so now let's look. So today the focus will be here, right? Identify the problem. So what we're going to do today is we're just going to spend the rest of the session today just looking at thinking of problems, making up abstract problems, and going into that pipeline from abstract problem all the way to about here. I might skip a few boxes in between when we're doing this problem, but my goal today is to identify a problem and then we get that. You know, and the question here is what should the data look like when it gets to this box? in particular for supervised learning, okay? That's really the goal. And that is, I cannot stress enough how that is one of the most important aspects of this whole process. Sometimes some of the other things are easy, actually. Okay, so it turns out that once you understand the machine learning algorithms, this could be easy. Okay, this actually, you know, it's almost like this. Once you gain experience and you practice a lot and you've developed your toolbox, your tool set of machine learning algorithms, this starts to become somewhat easier, or at least consistent. Whereas this area here will always be variable, because that will always require you to do work, because every time, hopefully, you'll be doing different problems, right? Or taking the same problem but with new elements, trying to improve it in some way, etc. So that's really the idea there. Okay, so let me erase this. I don't want to make it too messy. But the last thing I want to mention here, I've already kind of motivated what we're doing today. And so I really just want to say, so now, you know, you collect the data. And how do you collect data? You have to get it, you know, maybe you get it from social media. And how do you do that? You have to build a web crawler of some kind. Or you have to do something called scraping. These are topics that I cover in the applied machine learning course, right? Getting the data from social media, for instance, or collecting it from images. So you go to the internet, or you just take pictures, right? You have, let's say you're doing face recognition. Well, you're going to have to take pictures of all the people involved in your business or project. But basically, you're collecting the data of some kind. And the data can come from anywhere, right? Anything. Sensors, it can be from books, encyclopedias, you know. Obviously, the internet is one thing that has tons of information, so a lot can be found there. Feature engineering, that's what we're going to do today, okay? Feature engineering is this idea of taking a problem and framing it into a structure. Usually that structure can be called the vector space model. And the idea with the vector space model is that every sample, remember, a sample is the one thing that you're analyzing for your problem. So every sample can be represented as a point in a space. Okay, so let's say that I have a three-dimensional space. I have this point. This point is represented by coordinate F1, coordinate F2, coordinate F3. So I have three values that, you know, I go and then I find the position of that point in the space. That's called a vector space model usually. We'll be doing this in a more intuitive way today, but what I'll show you, I'll show you pretty much that. So that this will be the focus today. Pre-processing, as I said, once you have some kind of a data set, you continue. Let's just say here you clean the data further, right? You make some, and you make, oops. And usually when you have data, what you can do is you can apply any kind of transformation. We will actually see a little bit of that when we get into singular value decomposition. So singular value decomposition will allow us to give some intuition and actually look a little bit at you know, the vector space model and the math that can help us to do that a little bit more. Scaling, I already mentioned scaling, right? So I gave the idea of just making everything in the range from 0 to 1. So all features, all F1, F2, F3, Instead of each one going from 0 to 65,000, 0 to 1,000,000, 0 to 20, you make them go from 0 to 1. So they all have to fit within that scale and be proportional as a percentage from 0 to 1. This is just really important. So I'm going to put, you know, important here. It is always recommended. Maybe there are some data sets that are so straightforward that they don't need it really. But in essence, once you start getting into real data sets, it's always recommended that you do that. And I'll show you guys some of the math of how this is done this semester, again, because it's a foundations class. Now, keep in mind, a lot of the things that I'll show you, like the algorithms, etc., even though we're looking at it from the point of view of foundations, when you take 520, if you take it later on, for instance, you will see that some of those things now you can just use a library. So maybe make a function call, and the function call will do the same job. But the great thing about it is that by taking foundations, you now understand what is being done in the background, and that can be very helpful as you start progressing in the field. Then when you do feature ranking, dimensionality reduction, these are topics that I will cover later in the semester. So singular value decomposition, the chi-square at least. And these are, again, algorithms. And we most likely will not have time to cover something called principal component analysis. So that's a somewhat more difficult topic because it uses something called eigen decomposition. So I will probably not cover this one this semester, but it would take just too much time, I think. But it is part of this area. It's another dimension. These two are dimensionality reduction techniques, whereas this one is a feature ranking. Chi-square and information gain are two of the top. And I'll show you, for instance, we'll go over the algorithm, the technique, but I'll show you, and a lot of these things, you know, I will always mention, well, in sklearn, you can do it easily like this. In Weka, you can do it easily like this. You know, TensorFlow, PyTorch, there are so many tools out there nowadays that you can use. Python, the R language, etc. You can do all of this also in, you know, Hadoop and Spark with the libraries that they have there. All right, so anyway, so this shows some of the topics there, and so that's what I'm doing. So you can see here again, I'm just tying these with the calendar. Well, you can see there, singular value decomposition is there, dimensionality reduction, and so on. Okay, once the data set is ready, what that means is that the data set is now, and that's one of the things that we're doing today, is that a data set is especially in supervised learning, it's always made up of the, let's say the X matrix, right? The X matrix, actually that's a vector. So the X matrix and the Y vector, okay? So we're always going to have an associated X matrix and an associated Y vector. And this is what I'm covering today, right? Or is a topic that I want to make sure is clear, really, even though I might skip some of the boxes in between. The key thing is that you go from this input to that output, okay? That's the first phase of all of this, okay? And so that's what I want to stress. And I'm going to give you a homework assignment for this one, you know, with just a few problems. And I want to see you do this and just master it, you know, master the terminology and master how to do it. It doesn't have to be perfect, but, you know, you can do it. All right, so once this is done, which is what we're covering today. Let me go back to blue. Okay. We get into the machine learning algorithms. Okay. And when we get into the machine learning algorithms, you know, that brings in K and N. My space here is becoming smaller. Right, that brings in, we'll start with K and N. K and N, you've heard me mention it many times. It's called the K nearest neighbor algorithm. I'll start with this one because I think it's the easiest to understand, the most intuitive. Okay, it's the most intuitive. And so these are all for supervised learning, for classification, right? Remember, classification. I want to predict a label given a sample. Is it a cat or a dog? Is it a boat or a car? Should I go left or right? You know, should I hit the brake? You know, that kind of thing. So the algorithms, there are many. I will, you know, my intention is to cover KNN, naive Bayes, to look at actually how those algorithms work. And then in particular, the perceptron, which leads to neural nets, just because they're so important. We'll spend a lot of time on neural nets this semester, maybe 2-3 weeks. And that's just because there's a lot of background that goes in there, because neural nets themselves have several algorithms associated with them, right? Because this is where the topic of optimization comes in. And you guys, you know, just, we all know intuitively what optimization is taking a problem and finding the best solution. So for a neural net to be a good model, we have to find some parameters. And so we're going to look at basically something called the stochastic gradient descent algorithm. And that is associated with algorithms called backpropagation, feed-forward algorithms. So we'll take a look at those. I don't plan to build an entire neural net that involves all those algorithms working together per se, because that's impractical actually, and you should never do that, given that your code will always be slower than what the frameworks have built, right? So, and when it comes to this, speed becomes important as you start doing big data. But we will go over the fundamentals, right? So we will go over, you know, that's actually one of the main objectives of this course, is to cover neural nets and that whole framework of, you know, you never know what's going to happen to, you know, think about business and how it is. You never know when TensorFlow or PyTorch could become services that you have to pay for, and then they become more expensive and more expensive. I doubt that will happen, but it's just an example. So at some point, you fall into the problem that it's just not profitable to you anymore to use those tools. But as it turns out, you took 365 and you remember that really that's just some algorithms, and so you could start building your own. That's really the point. So I will point out really what that entails, you know, but we need to look at the background before. So I don't want to get too into that right now. I just wanted to point that out. So KNN, naive Bayes, very easy algorithms. The perceptron itself is very easy and straightforward. Then we get into neural nets, which, you know, are a little bit, are the power, neural nets and deep neural nets, right? So if you understand neural nets, understanding deep neural nets is easy, but just know that they are a complex machine. And so they require a little bit of other algorithms that allow them to work. They are related to algorithms like logistic regression and linear regression. So if you guys took your statistics course already, you probably looked at linear regression. So you have some intuition of that. And actually, it turns out that all of these are kind of related. So we'll talk about in general about, you know, these are the algorithms, maybe support vector machines. But just be aware, these algorithms that I just mentioned, they're only a handful of the many that are available. There's decision trees, random forests. I just don't think I'll have time to cover, you know, every single one of them, okay? And so, but that's why I'll just say dot, dot, dot. That's where they fall in. And that's why this is called a pipeline, right? So all these little elements in the pipe can be replaced. And this actually applies to, I guess I should stress, this also applies to unsupervised learning, right? So in unsupervised learning, I wouldn't have labels, but I would probably have the same pipeline here for the data. And the algorithms, the one that we'll cover in the class is called k-means. So I will go over this algorithm this semester. And if time permits, I will cover GMMs. If you notice in the syllabus, they're actually like the last topic. They're called Gaussian mixture models, and they're supposed to be more powerful. Okay, and so that's so this is unsupervised, right? Over here, that's unsupervised. Down here is mainly supervised, okay? But we also mentioned that there is reinforcement learning and sequence mining, right? Reinforcement learning and sequence mining. So in essence, if you keep the pipeline the exact same for all four, then basically it just means that here for reinforcement learning and a sequence mining, we have other algorithms as well. And I'm running almost out of room, but let's just say up here, oops, that's not, let's say, up here, for reinforcement learning, the algorithm is called QLearn. And we'll go over that algorithm for, as I said, for the taxi cab problem. So that taxi cab is a very fascinating problem, so we'll take a look at that. But that would be the algorithm. And the last thing for sequence mining, which is a type of problem where you have sequences of data, right? So remember, I know the weather today, tomorrow, and the day after. But remember that the weather on Thursday or Friday isn't in a way related to the weather today and tomorrow, right? Because it's the same, weather is, the cloud system and everything, how it's moving. And so they're related. So it's data that it's not independent data, right? It's data in a sequence that's dependent on the previous data. All right. And so for that one, we will cover something called the HMM. You can see that, which stands for the hidden Markov model. And you can see I do have that in here as one of the last topics somewhere in here. Yeah, hidden Markov models. And that involves the Viterbi algorithm. And so there, and then I'll mention some of the applications later on. And that's it, right? So as you can see, what I've done is I've tied everything in the calendar here. And I tried to explain to you why it's important, okay? How it fits into your course, right? Finally here, we'll talk a little bit about labels, right? What type of labels and classes you can have. So as you know, you can have classes like cat, dog, bunny, right? So that's 3 classes. So that's gonna be 0, 1, 2. Usually, something like that. It's gonna be numbers. But you could also have real valued numbers, right? So whenever you do linear regression, right? So I want to predict how much you spend, right, of your salary. So that's not, so if it was a labeling problem, I would say big spender, medium spender, small spender, right? So 3 classes. But if I want to predict the actual number, that's a real valued number. Like I want to say, oh, this is a person that spends $20,000 a year, $25,000 a year, 27. I want to actually get that number. That's a real valued number. And that's actually not a classification problem, but a linear regression problem, right? So that hopefully you learned that in your stats course, but as time permits, I'll throw that in there because actually the framework of neural nets, logistic regression, linear regression is very similar, very, very similar. There's a lot more similarities than you might imagine. And so we'll take a look at that, at least briefly. But anyway, in the context of the pipeline, you can have labels, you can have real valued numbers, you can have sequences of predictions. So I want to predict ice cream consumption for next week, all 5 weeks, right? Given weather. So my output, my labels would actually be not just, you know, high, low for one day. They would be high, low, medium for this day, followed by medium for the next day, followed by medium for the next day, followed by low for the next day. So it's a sequence of predictions, right? So the labels can also be sequences. And that's going to be, in deep learning, there's an algorithm for that called recurrent neural networks, but that's, you know, way more advanced. And I guess I should mention here that another algorithm is deep neural nets, right? Which are basically just an extension of neural nets. All right, so these are all the little pieces, right? And that's where all these little names that you'll hear me talk about during the semester, that's where they're all coming from. So I would strongly recommend, as I said, either print this or make it up you make it nice with a computer and just put it on your wall, you know, put it on your wall, push pin, and always keep track of where you are and why. That'll give you a lot of good context on the topic. And then finally, in performance evaluation, we'll talk about, you'll hear me talk about the standard performance metrics, accuracy. So accuracy, precision, recall, the F measure, the ROC curve that we will cover this semester, and the confusion matrix. So as it turns out, every time you run your data, you actually want to print out all these metrics at the same time, because they give you a perfect picture of what you're seeing, okay? They will give you a perfect picture of what you're seeing. Along with that, sometimes when you're doing these models, you print out visualizations of things, but that's usually only used for like academic purposes when you're learning, right? So when you're learning, you know, and you're taking a course, you'll see me, I'll create some graphs every now and then with matplotlib. But when you have real data sets, it'll be very difficult to visualize your data. That's in fact the reason why we have a course in visualization, right? So that we can look at all the tools for visualization. And so that course will, you know, with Professor Gurjin, that will help you out with that. Here, just for your understanding of the algorithms, I'll use visualization. But really, the way to visualize your data will be through these metrics, okay? These metrics are just numbers, but they will quickly paint a picture for you of everything that's going on. Okay? Okay, guys? All right, so this is, you know, I think this is a very important, you know, slide, and that's it. As you can see, that's pretty much the whole semester summed up into one slide. Turned out really well, actually. Okay, so now that concludes the part about the pipeline today. And so now what I want to do the rest of the time is basically do some problems. Remember this arrow in yellow. We're going to identify some problems, and then we will arrive at these X and Y data sets, right? So I want you to always think, what is the X? What is the Y? What are the rows of X? What are the columns of X? What are the rows of Y? Obviously, it's a vector, so it only has one column. You know, and what are the values? What do they look like? You know, are they consistent? You need to be obsessed with that, right? That needs to be your obsession in life. because a very good X and Y, you know, will increase the probability of your success. Remember that in computing, that old saying, right? Garbage in. How does that go? Garbage in,
Garbage out.
garbage out, right? And so if you have garbage in your X and Y, you can't expect your model to do magic, right? Your model can only, remember, models in labeled data, they learn what you show them. So they're really just learning to mimic you, humans, right? And so they can't do magic. So you have to have a really good, what do you call it? A really good definition from identifying problem to X and Y. Okay, so that's basically the pipeline as it stands. Are there any questions before we move on to the next topic? Okay, it sounds like there's no questions. Okay, let me get a cup of coffee here. Just give me a sec. All right, so now I'm going to move on to I'm going to move on. I'm going to save this actually. I think I have, let's see. Okay, so it saves it as a PNG. I just really like how this turned out. Okay, so I'm going to try, if this saved correctly, I'm going to try to upload these to the you know, either Brightspace or the website, and then you guys can, you know, maybe print them out from there. I don't think I can do a PDF. If anyone knows, tell me, but I don't know how to do that. Okay, anyway. All right, so let's move on then to now the next. So remember, the next part is now we're going to take some problems and we're going to arrive at the X and Y. And remember, the trick is once you have these X and Ys, you can feed them into any machine learning algorithm. That's my goal. That you create, I want to be efficient. I want to create a data set, and then I can feed my data to my own code that I wrote from scratch, and I wrote it in C, C++, or I wrote it in Python, or I wrote it in R, you know, or I wrote it in Scala, you know, different languages for different frameworks, or I can load it for the library of PyTorch. I can load it for the library of TensorFlow, Hadoop and Spark, Weka, you know, and even the AWS, Oracle, Google, cloud-based services, right? So basically that's the goal, right? That you want to do that data set and have it be generic enough that, you know, you want it to be generic enough that, or formatted in such a way that you can just load it on everything that's available out there. Okay. All right, so let's go ahead then and start. All right, so let me see. And this, you know, I'm going to ask you guys to participate in this one a little bit more. I will do the first one, right? I will do the first one, and then from there, you guys can participate. Sorry, I dropped my. You guys can participate, and we can solve. You know, and based on, I'm actually going to go based on your interest, right? So anyway, so now we focus on the part of the pipeline where we identify the problem, right? And we want to go from identifying the problem through the whole pipeline, right? So dot, 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 input, dot, dot, dot. But we want to arrive at X and Y, where X are the samples and Y is the labels. Okay? So basically, X is going to have a dimension n by m. Okay? So X will have dimensions x by n. And then the labels will have dimension, Y will have dimension n by 1. Okay, that's very important. So these two, notice they're the same. They're both n. So that is to say, if I have, let's say, 1,000 samples in here, I need to have 1,000 labels because every sample needs to have a label. So the rows are the samples, S1, S2, S3, dot, 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 Sn. Okay? Very important. Each row represents a sample. Okay? Represents a sample, each row. So although this is a matrix, every row is a vector. Okay? Now the Y is the labels. So you really just have one value per sample, but you have, Y labels. Now the M, so that just leaves the little m over here. What is M? M is the features, right? So usually this is, and this terminology, please, these terms, you need to know what they are. What is a sample? Which is basically a row in X. What is a feature? Basically a column in X, right? And then what is a label? Right, so it's basically one of these, right? A row of 1, right? So label 1, label 2, label 3, dot, 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 label n, okay? So that's basically the idea for now. We're just gonna think of this. Usually we're just gonna take a problem, save our data in a text file, usually in a comma-separated file, although there are other formats, but that will be the idea. So features then, you can have F1, F2, F3, dot, 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 all the way to Fn, or sorry, M, right? So it should be M. All the way to Fm, okay? And so that could be 100,000. You might say you're crazy that you can't have 100,000 features. Well, what about an image? Think of an image. If I have an image that is 28 by 28, right? So that the classic MNIST data set, this is an image of a handwritten digit, 7, right? Where these are pixels, they're like grayscale pictures, right? Pixels, sorry, and then the rest are just a white background. Well, if I wanted to represent this as a sample, one of those images, notice that I have to make it into a row, right? So what I can do is I can spaghettify, right, the image. So you know what spaghettify means. I take the image, like imagine like when you have a piece of cloth and you grab the 2 strings and you just pull them, right? And so what happens? You end up making that 2-dimensional into a 1-dimensional, right? You just pull everything. So that is to say this one goes there, this one goes here, this one goes there, and so on, dot, dot, dot. The last one goes there, right? So you spaghettify it, right? And then once you have that, every pixel in the image, every little pixel becomes a feature, right? So if we go back to this, MNIST, which is 28 by 28 in 2 dimensions, if we make it into a vector, what is 28 by 28? $784, right? 784. So we end up just right there with a tiny image, 784. And we actually have images that are much larger, right? I'm pretty sure a lot of the images just in your phone right now are much, much larger than 28. So think about how big that's going to get really quickly. You know, just do the math, a 300 by 450 pixel image and see how big that is. So is it 300 by 400? That's already 120,000. So pretty big. All right, so anyway, that's the way it works, right? So that's the way it works. So every time then we take a problem, I want your X and Y. This will be the whole homework, okay? So the homework, I will create a link and I'll provide I'll write a little text file there and give you 5 problems. I still want to think a little bit more about the problems, but once I give you these problems, you will tell me, you will give me this. This is the output that I'm looking for, okay? The X and Y, what are the labels, samples, features. Usually of this, the labels are the easiest to identify usually. You have images of cats and dogs, right? So cat and dog, pretty easy. Samples, okay, sometimes samples can be difficult. Like if you're in the network and you're trying to detect, build an intrusion detection system for machine learning. Well, do you use one packet? If you use one packet at a time, it's pretty straightforward. You just grab that packet. But sometimes it makes sense that instead of one packet, you actually take all the packets in an interval of time. Like you might say in a half a second time window, I want all the packets. Well, in that case, identifying what a sample is, that becomes a little bit harder, right? That might be actually a problem I give you in the homework, in your problem set today. It'll be between 5 and 10. I'm not exactly sure how creative I'll get, but be on the lookout for that homework, certainly by Friday. And then I'll give you, a week as usual. So identifying the samples might be tougher. Features will be the hardest usually. And that's where, remember that box that I had on here, right? Remember that box? Where is it? Feature engineering, right? This box here. Okay? Feature engineering is that part. There is no right or wrong answer. There's only worst or better answers, okay, for the features, identifying the features. There's only better or worst. At the end of the day, I always like to tell students this, right? So, money doesn't give, what is the saying? Money doesn't give you happiness, but it certainly helps, right? It provides security and all that. So if you're in a company that, is using machine learning for the stock market, what's your goal? You want to earn the most money, right? So if you pick bad features, well, you're going to get maybe some money, but the company may not do well enough. The better features you engineer, the more money you're going to make, right? And so it'll translate into, security, stability, all of that. All right, so anyway, so now we have S1, S2, again, Sn. This is M, so it's going to be F1, F2, Fm, and then the labels, let's say, for classes, label 1, label 2, label N. Remember, it has to be consistent. All right, so the best way to get through this then is to have a problem, right? So let's take a problem. Let's start with a classic example of images. So I'm going to start with MNIST. So this is MNIST. Okay, so in MNIST, you have 70,000 images. You have 70,000 images. That's just given. And you have 10 classes. The classes are the single handwritten digits, right? So the classes then are 0, 1, 2, 3, dot, 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 all the way to 9. So what does an image in MNIST look like? They're not in color, they're black and white, grayscale, 28 by 28. So I have an image and somebody wrote a 7. But then remember that some people write their, oops, I wrote the same way I was writing. Some people write their 7 like that, right? And then what about the person that writes a 5 and, you know, like that? And then there's the person that writes the 2 like that, but other people write the 2 like that. Do you see that? And what about the fact that this 2 and that 7 kind of look alike, right? What if you have a person that it was just kind of lazy and they just did, they maybe did, you know, they did, you know, and kind of here, they just kind of stopped like that. They meant to write a 2, but it for an algorithm, even something like that, right? For an algorithm, I mean, we're human, we have a little bit more, you know, capacity to discern things, but a computer, you know, might have a hard time. It might actually mislabel this as a 7, and rightfully so, right? So that's what MNIST looks like, okay? That's what MNIST looks like. We're going to take every pixel, and it's going to be a feature. So like, you know, F3, you know, F10, whatever it is, we're going to take those features, okay? So we have the information that we need. So now I need, don't worry about how would we do this in the code, you know, how do I code this, you know, that's just your coding abilities, right? That's just your ability. You can picture something, what the input is, what the output should be, and then you can spend hours and hours writing the code until you figure it out. So that, you know, that's not really the focus here. Instead, what I want you to focus on is what should the input look like? What should the output look like? So here then, I'm going to take these samples. These are the images. The name of the file will say, or maybe they're in a folder. So you might have a folder of all 7s, a folder of all 2s, a folder of all 5s, and so on, right? So basically that means, just here I'm going to say, the label is 5, the label is 2, label is 2, label is 2, label is 7. I'm going to erase this part here. And here, this one, the label is 7. I'm also going to erase, well, I'm going to keep the 28 by 28. All right, so I've got labels, right? Then I need to identify my samples. That's the next thing. So I'm going to say this is sample 1, sample 2, sample 3, sample 4, sample 5, sample 6. Okay, so now I have S1, S2, S3, S4, S5, S6, and you know this goes on for until 70,000. There are 70,000 samples, therefore there are 70,000 rows, okay? That's what I'm looking for you guys to identify. You have to give me, in the homework assignment, you have to give me these values. Okay? We know the labels, that's pretty easy. S1 is 7. S2 is 7. S3 is 5. S4 is 2. S5 is 2. And S6 is 2. Make sense, guys, so far? Making sense? Questions?
Makes sense.
All right, so this is example, remember, of the homework that I'm going to give you. All right, so I'll write a problem of some kind. And, you know, I might be a little bit, you know, generic on the problem, so I'll leave it to you to kind of fill in things. But I just want to see this process. I want to look at, you know, once you guys do these assignments, we'll discuss them and make sure that everyone, that this is very clear, okay? So now, the next part is, so we identified the samples. Each image is a sample. We know the N. We know the M. Oh, we don't know the M. So what is the M? You guys tell me. What is the size of M? So the features, right? How many, that translates into how many features do we have? So you need to tell me, how many, what is the size of N? M. How many features do we have? And what are these features? Those are the three questions. So what is the size of M?
Is it 10?
Not 10. 10 is the number of available classes, right? 10 is the number of available classes or labels. So it relates to the values that go in here. M relates to the value here, right? In the X matrix. This is the Y.
Are we using the 70,000 images?
We are using 70,000 images. You're correct there.
So what would it be? 700,000?
Huh?
700,000?
Nope.
10 times 700,000? It was 70,000?
That is not M. No.
Oh,
M is the features, right? M is the features. So the first question then is, what are the features of an image? Features are the things that represent the sample. So what are the features of an image usually?
like X and Y. I thought we were talking about the 7s and the 2s.
We are. The 7s and the 2s are images, right? So you know these are all images of size 28 by 28, right?
Oh, okay.
Right, so this is an image. It's just a picture, you know, like the pictures you have in your phone, right? So, but this is black and white. It's not in color, right? So remember, color would have R, a matrix for R, a matrix for G, B. I don't want to get into that. So let's just think it's a two-dimensional array. So what are images made of? Images are made of pixels, correct?
Correct.
So every pixel just has a grayscale from 0 to 255, which indicates the grayness, right? And that, you know, that kind of, if you're drawing more complex things, you know, that's helpful. Here it's just numbers, so it's actually just little lines. And so it's simpler, right? So the features in an image are usually the pixels, okay? So every pixel in the image is going to be a feature. And if you look over here, we're gonna use the spaghettify idea, right? So we grab first row of the image, and then we take the second one and concatenate it after. So we go from an image that is 2D to one that is 1D. But we don't want to lose any information, so we just, right, we go and we got to figure out what this value is.
784.
784, exactly.
Oh, I just misunderstood you were talking about actual pictures. I got confused with the letters. I thought you were just saying like either true or false.
No, I was talking about images. Yeah.
Got you.
So we'll, as I said, this is just one example. It's usually one of the more intuitive examples. So I'm starting here, but we'll take a look at other problems. All right, so 784, right? So once I've identified 784, that means I want all pixels to be features, right? Every pixel in the correct order. So always, you know, like the first pixel is F1, then let's say these are, you know, 28, so F29 would be the start of this one, and so on, right? So those features indicate which pixel I'm using. If you look, one key thing when you create the data set is that the columns are aligned. So for instance, this is F2, and that's pixel 2 in every image for every sample. So that tells you, for one thing, that all the images should be the same size. That's usually a a point of confusion for students. So what if I get all these images from the internet and they have different sizes? Well, part of pre-processing would mean that you have to crop them to all be of the same dimension. Let's say in this case, 28 by 28. Make sense, guys?
Yes.
All right, so I want to know, this is the important thing, right? So understand, M is 784. That means you have 784 features, which means then, as far as the data set here, you have 784 columns, right? So column F, I don't know, 100, right? For every sample should, in a perfect world, what you want is for every sample to have a value, okay? You want it to be a value. You don't want it to be a missing value, for instance, or a 0 because you don't have any data. That actually confuses the algorithm, because instead of thinking that there's no data, it's going to think that the value is 0, let's say. And that's actually not correct, right? It could be that the value is something else, but there was missing data. So in essence, you should always pick features that are present in all samples, okay? Make sense? So this is what I'm looking for when I say, what is X and Y? Questions before we move on to another problem? All right, doesn't seem like there's any questions, so let's do another one. Let's imagine that we're comparing trees, right? So we have a tree that looks like that, and this is not going to be pictures anymore, right? So, right, that's a tree that looks like that, and then we have a tree that looks like that, right? So we have 3 types of trees in a forest or whatever, Forest Service. So again, question is, and you have 100 samples of these. Now, you're not going to take pictures of them. Instead, what they give you is a tape measure. So you're going to take a tape measure and a questionnaire, and you're going to go out there and collect all this data, and you do that over the summer. You've collected information on 100,000 trees. That means you have 100,000 samples. About 20% of the trees are this type, about 50% of the trees are that type, and about 30% of plant life, whatever, is this other tree. So now, again, question is, I want to do machine learning classification to differentiate between these 3 types of trees. So what are X and Y? So again, in your solution, n by m, 1 by n, y, x. So you have to tell me. Remember, you're going to collect the data. There's no images. You didn't have a camera. You lost your phone. So all you had was a questionnaire and a tape measure. And actually, the person that told you do this, they also told you, you know what, figure out the features. I don't know, figure out. So you have to do it. You don't even know what the features are, so therefore you don't know the size of M. So that's why this is called feature engineering. You just have to figure it out. So again, let's do this. Let's start with the easy things, what information we can actually fill in, and then we can come back to information we don't have. So what information do we have? What data do we actually have? Guys, what information do we have?
The dimensions. The dimensions, you said that we had a tape measure.
You have a tape measure. You have to figure out the features. Nobody told you what the features are going to be, right? So you're going to collect it.
I'm saying we can collect the dimensions, like height, width.
Oh, okay. So those are the features that you're suggesting then, okay?
Yeah.
Okay. Features. So you're suggesting height. What else?
Width.
Okay. What else? Yeah, that's two, right? So you're just basically saying, I'm going to take a tape measure. Maybe I have a ladder. And I'm going to measure the height. I'm going to measure the width of the tree. So, you know, and you see patterns already, right? So these are probably going to be taller, but skinnier, right? These are going to be the widest ones and the shortest ones. So you already see the pattern. So those are, I would say intuitively, those are probably good, good features. All right. Anything else? Let's say there's 10, right? So there's 10 things that you measure. Because you also could take the height and the width of the leaves, right? The branches, the stem, the roots. So let's say they're just combinations of height and width of all those elements of a tree. And you arrive at 10 of them. Okay? 10 of those. Height, width for 5 things. Gives you 10. So now, fill in the values for X and Y. What are they? What is N?
Wouldn't that be 100,000?
100,000. Very good. 100,000. Excellent. Because there are 100,000 samples, 100,000 trees. Right? Like that. How many labels do you have?
3 labels.
3 labels, right? 0, 1, and 2. You can encode it, right? So we're going to say that this one is 0, this one's a 1, that's a 2. So the values are going to be 0, 1, 2, you know, depending on which sample tree you're looking at. And then we talked about the features as being height and width for stem, for the whole tree, for the root system. So what is the value of M?
Ten.
10. Very good. Because there are 10 features. So it's going to be F1, F2, dot, 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 F10. You see that? So let's say that F2 is the root, for whatever reason, F2 is the root height. Okay? So that F2 has to be the root height for every single one of the 100,000 samples. Okay? So that is called alignment. You need to make sure that that is correct. Otherwise, garbage in, garbage out. Okay, that's extremely important that you have that sense of, okay, yeah, F2 for every sample is root height. F3 for every sample is root width, for instance. Okay, and that's it. You see that? So it's not really that difficult, but it's a basic mechanism that you guys can take to have your data set ready, okay? To have your data set ready. Let's do one more, and then after that we can stop for today. And then, as I said, just look out for that problem set where I'm gonna ask you basically to do this, but I'm gonna give you different problems. So I'm gonna keep these very simple and short. Let's say that I have, let's say you guys remember the Boeing. Is that how you spell Boeing? The Boeing 737 Maxes, right? You've heard of them. Unfortunately, they had, you know, some accidents that resulted in the loss of life, 2 accidents, in fact. So the idea is that the planes, you know, they have a sensor, a little sensor here. The planes have an instability. The engine that they put is too big. It doesn't fit directly below the wing like the old engines fit. So they had to move it further in the wing. The problem with that is the planes, when these things are at full power, the angle tends to increase, this angle. And so the plane starts to climb, right? And obviously if a plane climbs too much, it's like a rocket, it's gonna lose stability. But they have a little sensor, all right? And that sensor tells it that that's happening. And so, the wings and everything, in the back, control the plane to kind of move it back down so that the angle is reduced, right? The angle is reduced, and then you have no, so it's a type of a classification problem in the sense, move the nose up, move the nose down, right? So that's basically what you want. So again, given this problem, let's say that somebody gives you a machine learning algorithm, asks you to build a machine learning algorithm, okay? Train the machine learning algorithm to do this. Go, nose up, nose down. Okay? That's it. Those are the two actions that you want to take, right, for the model. The model will look at sensor data, and based on that sensor data, it'll make the decisions. You also have a simulator, right? So in this thing, you're going to do this and not going to train it in real life. So simulator first, right? And you run again 100,000 simulations. 1,000 simulations. So that can be your samples, right? So I'll help you out there. 100,000 samples. Again, do the feature engineering and fill in all the values for X and Y. So what do you think? Again, I'm making these problems, if you look, more open-ended, right? So I just want to see how you think, because it's okay to fill in the blanks, right? You can make your own assumptions. So what do you guys think? You got to figure out, what is M? What is this N? This is 1. What are the labels? What are the samples? What will you do as far as the features, your feature engineering? So again, this is the same, type of problem, right? And this is what I will give you in the homework. So let's finish this one, right? So what is X and Y?
Well, Y would be nose up or nose down.
Exactly, nose up or nose down, right? So 0, 1. You could also call it -1 and +1 if that's more intuitive. That's a perfectly good label because they're still numbers, right? They're still numbers. And so this would be perfectly fine. 1, 1, right? So basically what this implies is when the sensors had these values, the correct thing to do was to nose, and I probably should have changed these. When you have these sensor values, nose up. That's the correct thing to do. And the plane learns how to do that in the simulator. Maybe there's a pilot involved or something, but you do it. So nose up is +1, nose down is -1, given the features. The samples, you just run 100,000 examples of that, which means this will also be 100,000, right? So now you have samples S1, S2, all the way to Sn. So again, as you can see, usually the hardest part is the features and M. So what do you think? What could be the features for this?
Like the degrees of the angle.
Degrees of the angle, right? Very good. So you have some kind of a sensor. We don't have to get into the physics of that or whatever. We just assume we have some sensor. And the sensor measures this degree. Let's call it the angle of attack degrees. Or actually, angle of attack covers it, right? So let's just call it the angle of attack. So that sensor, angle of attack, measures that. But we usually don't just want to, even though that might be the best feature and the only one we need, just for completion, let's think of a few other ones. What do you think? What are a few other ones?
The weight of the plane,
The weight, very good. The weight of the plane, right?
the air resistance,
The altitude, maybe.
The what?
Altitude.
Altitude, perfect. The speed, right?
speed.
Exactly. Very good. Very good.
So all you know, like in a car, right? These are all things that we can get from the dashboard. So basically, we could have all those. They become the features, right? F1, F2, F3, F4. And in this case, let's say that's all we need. So we have 5 features. We have 5 features. What is the size of M?
5.
5. Perfect. And then F1, F2, ... F5. And just keep in mind, if column 1 is F1, which is the angle of attack, that degree that you mentioned, then that column angle of attack has to be the same for all samples. Do you see that, guys? And that's it. That's all I want you to do in this assignment, is to figure this out. So be on the lookout. Very good. I think you guys are getting it. So be on the lookout. There will be between 5 and 10 problems. I'll look them up. And I will ask you basically to do this, and then you will submit your report. Okay? All right. So are there any questions before we sign off for today?
No questions.
Questions. All right, guys, great. So then, as I said, we will meet again. Oh, there's no class on Monday, right? So there's no class on Monday. So then we'll meet again on Wednesday. Probably introduce KNN at that time, and then you'll still be working on the homework assignment, which will be due like Friday, given that I'll post it. I'll try to post it by today if I can, but certainly by Friday it'll be there. Yeah, and that's it. All right, so we'll stop here for today, and I will see you guys next Wednesday. Have a good weekend.
Or your weekend.
Have a good one.